Hello everybody, and welcome to another lecture of 6838. As always, it's a pleasure to see you all virtually and to tell you about some more fun topics in the world of geometry. So today we're going to begin our exploration of one of these topics that really could occupy an entire course, and in 6838 we dispose of it in like a lecture and a half, and that topic is vector fields. Specifically, by the way, when we talk about vector fields on surfaces or on manifolds, I really mean tangent vector fields for the most part. So just an assignment of a vector to every point on a geometric domain. And we're going to see that there's so many different applications for this sort of machinery. Before we get started, I thought I better mention that many of the slides from today's lecture and for our next lecture, which will be on vector field discretization, are borrowed from a few different sources. Mainly from a course on vector field processing on meshes from SIGGRAPH 2016, which also has really beautiful course notes. So I encourage you all to download those, give them a read, or at least kind of page through to see that there's, 60, 70 pages worth of interesting material. And this is a very active and changing research field. Now, of course, in 6838, I'm not satisfied with just doing the graphics applications. So we'll also discuss a few applications in the machine learning world, both in lecture, mostly in the next lecture a little bit, and I may record an extra lecture segment specifically focusing on one interesting emerging topic called normalizing flows. In addition to this, I thought I'd point out one other nice reference in the literature, which is on directional field synthesis, design, and processing. So we'll mention at the end of today's lecture what a directional field is, but it's sort of a generalization of a vector field where you can have more than one vector per point in the tangent plane. And this is just a nice place to go look for some background reading and so on this particular topic, which is one of the most popular ones to study right now in the geometry processing universe. So with that, let's get started by motivating a bit why we care about vector fields and some of the applications where they appear. Now, as you've probably figured out in this course, thanks largely to your instructor's background, and also just based on one of the major applications of geometry and applied differential geometry and so on, one of the major applications of vector fields really is in the computer graphics domain. And vector fields show up all over the place in computer graphics. Everything from designing where you might place hair and fur on an animated character. Here we see, Remy from Ratatouille, I believe. To guiding tasks like texture synthesis, like what's happening on the bunny here, to meshing, which we'll talk about a little bit more later. So in the meshing case, maybe we compute a vector field on a surface, which is going to guide how we place these mesh elements later on in some meshing pipeline. In fact, let's zoom in a little bit on just that third picture and think about it a bit more. So one of the really major sets of applications for vector fields is in simulation and partial differential equation. And really, this comes up in two places. One, which I'm not showing you on this slide, is that vector fields are really the basic objects of manipulation in things like fluid dynamics, right? So if you look at the Navier-Stokes equations or whatever your favorite physical equations are for fluid flow and other sort of continuum mechanics phenomena, almost all of them are guided by vector fields that tell you things like velocity, momentum, and so on. A separate application of vector fields that I do show you on the slide here and is also relevant to simulation is in the meshing world. And this is an idea that really has been developed specifically in the computer graphics community for quite some time now. The basic idea is that we're going to compute an object that we call a frame field, where now maybe instead of having one tangent vector per point on a surface, you have like two that form kind of an X pattern or something like that, like what you see on the right-hand side. And then one of the very first steps in extracting things like hexahedral meshes, which is on the left-hand side, and quadrilateral meshes, like on the right-hand side, for volumes and surfaces, respectively, is first to compute something called a frame field, like on the left, which is going to kind of guide us infinitesimally how to place these discrete elements for these meshes. And now in this course, on most of your homeworks, you've dealt with meshes that are triangle meshes, or the volume version of a triangle mesh would be a tetrahedral mesh. There's this entire other universe of meshes, which are hex and quad meshes, like what you see on the slide here, which have a lot of really favorable properties from the perspective of like convergence of your discretization and so on. But there's an underlying geometry problem, which is how to extract those meshes to begin with. And one of the popular approaches is using this sort of frame field idea. So you first compute a smooth frame field, which is kind of like infinitesimally where you're going to orient your mesh elements, and then you solve a parametrization problem to extract the actual discrete pieces. So in the course notes, or I guess in our case on the course website, I'll give you guys some pointers to some research papers that introduce this procedure in a little more detail. But the really key step here is just computing a nice smooth field, which is going to be used to orient the elements later. Now, specifically for this application, there are many other concerns like integrability, which come up, which we probably won't get to in this course. Now, like I mentioned, of course, vector fields are really important for simulation, and simulation isn't just, a movie effect. It shows up everywhere across computational science and engineering. Another place where you see vector fields treated very carefully is in biological science and imaging, also in visualization, by the way, where I want to understand precisely, for example, in this particular image, the fluid dynamics of blood flow. Like does your blood flow faster in the center of a vein or on the outside or what have you. So basically, any time that you're doing almost any sometimes we call them in silico experimentation, somewhere hiding inside of there is a vector field. And indeed, it actually appears not just in the sort of obvious physical setup, but also in other areas of imaging. So for example, in diffusion tensor MRI and other MRI modalities, what you're really sensing is like the ability of blood to flow in different directions in different points in the interior of your brain or whatever organ you're imaging. In which case you might get some object which probably isn't exactly a vector field, but has sort of vector field-like properties. So for example, in the diffusion tensor MRI setup, I think you will usually get a diffusion tensor at every point, which is sensible given the name, which basically is like a semi-definite matrix at every point in a volume that tells you sort of where blood likes to flow. Disclaimer, I'm not an expert on these medical imaging modalities. Of course, vector fields show up in weather modeling. That's no surprise. Basically, this is just another byproduct of using vector fields for physics. One of the fun things is that, of course, some of the rudimentary models for weather that are zoomed out at the kind of scale that you see on the slide here really do operate kind of on two-dimensional, like Earth surface style vector fields, rather than worrying about the volumetric problem, although, of course, the volumetric effects are really critical for getting weather modeling correct. Vector fields also show up in applications like vectorization. So vectorization is the task where you take something like the line drawing, like the elephant on the left-hand side. I think this is just a photograph of a sheet of paper where somebody has sketched out this happy walking elephant guy. And the task is to come up with a sparse set of vector curves that covers this character and is a different way to represent the image. So rather than storing an image as a big grid of pixel values, now we're storing it like a sparse set of curves that cover the main lines that have been drawn by an artist. This task is a really valuable one. A lot of people would prefer to draw their vector art by hand, but at the end of the day, we want this vectorization, like on the right-hand side, so that we have an infinite resolution image. Right? If I zoom in really close to the elephant on the left, I'll see a bunch of pixels, like little squares. But if I zoom in really close to the image on the right, it'll still look smooth, right? Because it's covered by this sparse set of like Bezier curves or something like that. So one of the ways that people compute vectorizations of line drawings and other images is to compute a frame field or a vector field that's aligned to the image, and then to kind of think of these vector fields as flow lines of that, to think of the vectorization as a set of flow lines from the vector field. Now, in the particular image that I'm showing you here, this is actually from some of my own research with Misha Bezmeltsev, who's now at the University of Montreal. Basically, rather than using vector fields, we're using frame fields so that we can capture junctures better, like where two curves meet up and make a right angle or something like that. But that's more of a detail. I mean, the high-level idea of using vector fields to guide vectorization has been around, I think, basically since the beginning of the vectorization problem. I guess we've already mentioned this, but of course vectors fields are everywhere in simulation and engineering. Here you're seeing fluid dynamics for some version of an airplane simulation. And then finally, I thought I would highlight kind of a fun application of vector fields completely outside of the graphics domain, which is in the world of continuous normalizing flows. So the basic idea of a CNF, which I think I'm going to try and cover a little bit more of in an extra lecture segment if I have some time later today, looks something like this. Basically, I'll have some data set that I'm trying to explain. So maybe I have a bunch of data points that are kind of bimodal like that. And the idea here is that I'm trying to solve some kind of a variational inference problem where I'd like to cook up a sampler which can randomly draw samples from a distribution that kind of looks like the data that I've observed. Now, there are many different ways to do that, and this is a long-standing problem in machine learning, Bayesian inference, and other areas. But in the continuous normalizing flow universe, what you might do is say, well, I don't know how to sample from this distribution. In fact, maybe I don't even have a smooth distribution function. But one thing I can do is sample from like a Gaussian distribution centered at some canonical point. So in the continuous normalizing flow universe, one thing you might try to do is parameterize a vector field, where what I'm going to do is draw samples according to this simple Gaussian distribution, like what I'm drawing you here, and then learn a vector field, which is going to take these samples and kind of advect them into positions that are better aligned with the actual data that I observe. Right? So in this case, the vector field is really like a flow, which is giving me some path where samples can start being samples from Gaussians and end up being samples from this more complicated distribution. The vector field itself is parameterized in kind of an interesting way, which is actually using a neural network. So in any event, this is sort of an emerging application, and one of the questions that I have for all of you as graduate students in our department is whether any of the insight that we'll cover mostly from the computer graphics and vision world on really advanced methods for vector field processing can help us for some insight into these more kind of high-dimensional statistical learning applications. I mean, this is a pattern we've seen a lot in this course, but I haven't seen it specifically for vector fields yet. I'm hoping by the time I teach 6838 again in 2 or 3 years, this story will change completely and I'll have to throw away this lecture, but we'll see. And then finally, one fun application that's extremely practical of vector field design is in pastry design. Actually, every year my graduate students spend some time using vector field design tools to design interesting ways to weave the top of a pie at Thanksgiving. So here, for example, you see a singular point right at the center of a pie, and the design of this thing is guided by essentially looking at the flows of a vector field or a frame field. As always, I'm happy to offer negligible extra credit for students that make pies with interesting singular patterns. Here, I'm not such a great baker, so my singular pie only has one singular point in the middle, but you could try to make a pair of 2 canceling singular points and so on. In fact, in pastry design, one of the fun things to think about is that you also have to deal not only with the topology of your singular points, like the point at the center of this pie, but also you have to think about the weaving up and down to make sure that you don't end up with a double weave or something would be against the rules. Anyway, some really fun math problems and a good excuse to eat. All right, so there are so many challenges in vector field design, vector field processing, and so on, that we're just going to scrape the surface in this class, as always. But I'm hoping that in today's lecture and in the next one, you'll get some idea of both the kinds of theoretical problems that we think about in the applied domain for vector field processing, as well as some of the discrete approaches to designing vector fields in practice. And I think this is definitely one of these areas where there's no consensus, and it's going to continue evolving over time. There are so many different creative and interesting algorithms for designing vector fields, representing them, and using them in applications. And we see new ones come up every single year at SIGGRAPH, SGP, CVPR, ICCV, and many other different contexts. So we're just going to highlight a few, and this should not be considered a comprehensive lecture for sure. Okay, so our plan is just a big crash course in the theory and discretization of vector fields in 2 lectures or less. And I'm going to try and point out when we're skipping stuff as we go along. So today's lecture is going to focus mostly on the left-hand side. What are the interesting theoretical constructions, challenges, and ideas in the universe of vector fields, which is one of the basic objects that's studied in the world of differential geometry. And we're just going to introduce some of the sort of main keywords, buzzwords, and so on, so that you have some toehold into being able to read the big textbooks in this space. Now, again, if you read an advanced differential geometry textbook, like vector fields are introduced on day one and then used throughout, like the many treatments of Riemannian geometry and so on, right? So, for example, the sort of basic construction of a connection depends on differentiating and working with vector fields as sort of one way to understand almost all of differential geometry. Obviously, we're not going to get there in our lecture here, but my hope is to draw some schematics and help you kind of understand what these ideas are in differential geometry and why they're so darn important. So to get started, of course, we should remember what our enemy is and make a few definitions. In particular, we need to remember what a vector field is in the context of manifolds and so on. So if you'll recall, way back when, we defined an object called the tangent space to a manifold. And we actually sort of defined it two different ways, where really we defined it one way and then proved it was equivalent to a second definition. So the first way that we define a tangent space at the top here, this TPM, so M is your manifold, is to think of it as the sort of initial tangent vector of any curve going through a point P where the curve is constrained to go along the surface. Now, the second equality here is just sort of a second equivalent definition where we can also think of the tangent space of our surface M, or our manifold M, as the image of the Jacobian dg of the local parametrization of our manifold around P, right? So if we take a little map from our parameter space into the manifold and then differentiate it at 0, what we're going to get is the tangent plane. And unsurprisingly, these two things are basically the same. So one kind of notational headache here, which turns out actually to be the tip of a really interesting iceberg. But one headache is that there's a different tangent space at every point on the manifold. And so sometimes talking about things like tangent vector fields gets a little bit cumbersome in this notation, right? We're used to thinking of functions as a function from x to y. But if you think about a tangent vector field, then sort of it's a function from points on M to tangent vectors, but the space of tangent vector is different at every point. So it's not super clear how to write a map from x to y in that case. So differential geometry people cope with this by making a few additional definitions. So in particular, what we can define is an object called the tangent bundle. Now the word bundle appears all over the place in differential geometry, and you can kind of think of it as attaching a space to every point on a manifold and then gluing them together to make a new manifold. So in this particular case, we're going to call the tangent bundle Tm of a manifold M. By the way, I guess I got rid of the script M here. Hopefully you guys can read along anyway. Notice that there's no longer a subscript P next to T anymore. Right? So this is somehow describing the tangent space of the whole darn thing all at the same time. And the tangent bundle of a manifold is kind of like these pairs P comma V, where P is in our manifold and V is in the tangent plane at P. Okay? So the tangent bundle is this kind of interesting object. For example, if M is a two-dimensional surface, then the tangent bundle you can think of like a four-dimensional manifold, right? Because the first two coordinates are P, like the point on the surface, and then the next two coordinates are V, which is a vector at a point P. Okay, so if you're willing to buy this definition of a tangent bundle, here's a nice illustration of it on the bottom left, then you can think of a vector field as a map from our manifold M into the tangent bundle Tm, but with a constraint, which is that at a point P, we have the constraint that the second coordinate V is in the tangent plane at P. So I think all of you could basically buy that this is a reasonable definition for a tangent vector field, right? It's basically, I think, what we would guess anyway, just after introducing this kind of funny object called the tangent bundle, right? Where essentially what is a vector field? It inputs a point on M and it outputs a vector. But to kind of cope with the fact that the tangent space changes at every point, we're going to deal with that by, instead of just outputting a vector, basically inputting p and outputting p also as the first coordinate. Okay, so a vector field formally is really an assignment of a tangent vector per point, but sometimes people talk about it like a point in the tangent bundle, which sort of remembers what point your vector came from. I think I've managed to talk about this in a giant circle, but probably everybody in this class is smart enough to just read this slide and kind of get the basic idea. Now, for our treatment in this course, this sort of definition is going to be pretty intuitive and not something that matters a whole lot. But later on in differential geometry, you can actually put like a geometry on the tangent bundle itself and work with that as its own manifold. And this provides some really interesting insight and very slick notation for a lot of useful constructions. So we've already encountered some vector fields in this course. So for example, recall that we define, scalar functions on a manifold in a pretty simple way, right? A scalar function is a function that inputs a point on our manifold, like our bunny, and outputs a number. So for example, the color on the bunny here. And given a scalar function, one thing that we've derived in this course, for example, when we were defining the Laplacian operator, is the gradient vector field of our function f, right? And so we got there by sort of taking two steps. The first was to define the differential of our map, right? This is like, well, differentiating our map, in this case just into the real numbers, which I can get by composing with a curve, kind of similar to how we define tangent vectors. And then in our first lecture, or maybe our second, I don't remember, on the Laplacian operator, we showed that for every differential, there exists a tangent field, which is called the gradient, which is just sort of the direction of steepest ascent corresponding to our function f. Now, I think all of us kind of knew this intuitively. It almost feels like a tautology given our college calculus. What's new here is that our gradient vector field is tangent to the manifold. Right? So you've all computed gradients forever in Euclidean space. Now we're just basically showing that if you have a scalar function on a curved domain, you can come up with a tangent vector field, grad f, which is kind of like the gradient of a function, restrained to just be on the curved space. And now the gradient vector field doesn't need to know about extrinsic space. It's just tangent to the manifold. Now, gradient vector fields are nice, and notice sort of our very first example of a vector field on a domain is obtained by differentiation, right? Like basically, we started with a function, we differentiated it, and that's what led us to a gradient, which is our first example of a gradient vector field. Now, one of the really deep questions that we can study that really motivates some of the basic constructions in Riemannian geometry is to differentiate not just scalar functions, but actually vector fields themselves. This shows up all over the place. I mean, if nothing else, we think about, the spatial derivatives, div, grad, and curl of vector fields all the time in physics and so on. And if we want to design things like smoothness energies for vector fields, that's going to be really important. So remember when we define the Dirichlet energy of a function on a manifold, essentially what we did is we computed the gradient of the function and integrated its norm to get some idea of how quickly it's changing over our domain. One of the sort of central ways that you might design a vector field would be to go through a very similar process, right? Like figure out how quickly the vector field is changing along your surface or your manifold, and then take its square norm and integrate it as some objective function for optimizing for a vector field. This turns out to be a bit of a tricky matter because it turns out there's no single way that makes sense to differentiate a vector field in every possible application. We'll see that actually it really depends on the context. And so this basic question of how to differentiate a vector field, or a co-vector field sometimes, or differential form, or many other objects that are sort of related to vector fields, really is the tip of a giant differential geometry iceberg and or nightmare, depending on your perspective. Which in some sense really motivated modern differential geometry today. So, rather than spending the 3 months that it takes to really develop this topic carefully, we're going to do so in, half a lecture today. And so I really do think it's worth kind of just a little bit of a warning or disclaimer here, which is that this is a really common point of confusion in differential geometry theory the first time you see it. And I think it's a bit abstract. So ask lots of questions of me, put things on Piazza. And, one thing you should know is it's a common point of confusion for your instructor as well. So, many times I'm probably going to send you to your TAs who are more capable vector field processors than I am. Now, when we asked how to differentiate a scalar field or a function on a surface or on a manifold, the answer ended up being kind of very clear-cut and easy to follow. When we ask how to differentiate a vector field on a manifold, I guess in another vector field direction, unfortunately for us, the answer is that it's kind of complicated to do this. That basically, there are many different notions of how to differentiate a vector field that make sense in different applications, both mathematically speaking and computationally. And when you start thinking about your derivative, you're going to need to do a little bit of engineering and a little bit of math to figure out what really makes sense in your context. So this is one of these complicated stories that I'm going to try to make a naive attempt to summarize very quickly, and we'll see if we get you any kind of intuition at all by the end of today's lecture. So the basic challenge when I'm trying to differentiate one vector field in another vector field direction is that we need to identify different tangent spaces, right? So what is a derivative? It's sort of like taking something at one point, taking something at another point, subtracting the two and looking at the rate of change as those points get closer to each other. But there's sort of two different issues. One is we can no longer just displace along straight lines like we usually do when we talk about differentiation. It's pretty obvious how we're going to cope with that, right? By taking curves along the surface rather than just straight lines, like dy, dx, the dx is just no longer a straight line anymore. But there's a different issue, which is that usually, when we talk about dy, dx, the dy is obtained by subtraction. But here, the y's are like vectors in two different tangent planes, like what you see here. And you need to figure out what does it mean to compare vectors that are at two different points on a manifold. Now, in 6838, maybe that doesn't feel like a big deal because our manifolds have been embedded in Rn for simplicity. But for example, in the Riemannian case, there is no space where your vector field or your manifold is immersed, right? It's not sitting in some Euclidean space. So you can't resort to subtracting coordinates of things in 3D to deal with two-dimensional surfaces because there is no 3D. There's just only the two-dimensional world in front of you. Or to go back to this analogy that we've used many times in this class, let's say that I'm an ant crawling along a surface and all I see is this two-dimensional kind of differential world in front of me. I can still observe tangent vector fields very easily, right? They're just like little arrows that are sitting on the ground. But now if I want to differentiate a vector field, I have no three-dimensional space outside of the surface to work with, and I still want to come up with some reasonable notion of a derivative. This is sort of an abstract problem, but it really is sort of the key critical issue when we start talking about what it means to compute this sort of derivative. And so what ends up happening is that there's not just one derivative. I can't just say dx of y, where x and y are vector fields. Sadly for us, there's actually at least three. And actually, I think there's many more. And in fact, in some sense, you can develop different theories of differential geometry by defining different derivatives of vector fields in terms of each other. This is a very deep topic. For example, if you kind of read, I think, Spivak's treatment of differential geometry, this is kind of where he starts. There's this crazy Peter Peterson book also kind of has a similar flavor, but I find it terrifying. In any event, there's actually at least three notions that are listed on the slide here. One is the differential of a covector or a one form. I'm going to defer on this first one until we talk about exterior calculus. Unfortunately, given time constraints in this class and the fact that my colleague Keenan Crane does a much better job of exterior calculus than I ever will in this course, I've kind of deferred it in 6838 since it's all online anyway. Just go to his YouTube channel. But maybe I'll record one or two compressed lectures as just extra content to give my own perspective on that topic. For now, we're going to skip it and kind of defer to that universe. But we are going to talk about two other notions of differentiating vector fields. One is called the Lie derivative. Again, Lie is Lie in differential geometry, named after a famous mathematician, which is sort of a topological notion of derivative. It actually doesn't involve the metric structure of your domain at all. And then a second one called the covariant derivative, which involves the metric structure a lot and is basically I think kind of if we were to cook up a notion of a derivative of a vector field on a surface, what we'd probably think of. But it turns out to be the really critical construction for like how to generalize the notion of curvature to higher dimensions and so on. So we're going to try and sketch out the need for at least these two derivatives on the bottom here. And really, you should think of today's lecture as just motivating. Hopefully I've done enough of a job talking down today's lecture to make sure you understand how informal and sloppy it's going to be. So before we draw pictures and really work out the details of some of the different notions of differentiating vector fields on manifolds, I thought I would just sketch out a sort of high-level story that motivates why we at least need these two ideas. The basic idea or point here is going to be how we can take some simple notion of a derivative we know from calculus and dig into why engineering a derivative of a vector field on a curved domain is so tricky. Incidentally, this story I'm basically borrowing from a Stack Exchange post that I found online that I thought was a really nice way to kind of frame the story here, at least for us engineers. So let's move that up into the corner. Oh, that's kind of annoying. I have that URL in the corner. Let me get rid of that. So here's the basic point when it comes to engineering the derivative of one vector field in the direction of another vector field. So basically, here's what we need to figure out. You know, we're trying to compute some notion of the derivative of a vector field. By the way, we often abbreviate this as VF. So let's start with how we might do it in Euclidean space, and then see where things go a little bit wrong. So here, maybe I use this generic kind of letter, you know, big D here, to refer to differentiating a vector field y in a vector field x direction. So I have a pair of fields in, maybe to start with Euclidean space, and I want to know the rate of change in the x direction. So in Euclidean space, I think we could all agree that it would look something like the following limit, right? So basically, you know, if I'm trying to evaluate this at some point p, right? So maybe I'm at p. This would look like basically the definition of a derivative. It's also what's on the corner of the screen here, right? So I would take the limit as t goes to 0, not p. My apologies. I hate this board. Okay, that's only a little messy. Okay, so it would be the limit as t goes to 0 of, you know, the vector field y evaluated at p plus t times x, right? Because this is the derivative of y in the x direction. By the way, I guess this is like x evaluated at p, but I'm not going to write it explicitly here, just for simplicity. Minus y of p divided by t. Okay, and this is a completely sensible definition in Euclidean space, right? Like if I think of vector fields in Euclidean space as just maps into, you know, from Rn to Rn, then this is a perfectly reasonable definition, and it actually will agree with basically all of the definitions we'll cook up, or at least with the covariant derivative. I think with the Lie derivative, something is a little bit different. Now, why is this a little bit funky when we're talking about vector fields on curved domains, right? So now, you know, maybe I have my favorite manifold, like this donut here, and I have vector fields which, you know, you can think of their flow lines like little curves along the surface, are constrained to be tangent, right? So maybe this is x, and then there's some other field which is, you know, circulating around and is y or something. This picture isn't terribly helpful, I'm realizing. So from my perspective, there's sort of two things that go wrong here. One of them is obvious, and the other is a little bit less obvious because of the way that we've sort of set up our lectures in this course. So here's the first problem, is this p plus t times x, right? Which is that, you know, in general, I can't do this on a manifold, right? I can't just take a point p and displace it in the x direction linearly, because this is like, you know, taking a point on my surface, following a tangent vector, and I could end up like somewhere off of the domain, which really doesn't make any sense, right? So in other words, I need to replace this p plus tx term with something that needs to be on our manifold. Okay, And I think you can all sort of guess where I'm going to go with this, which is basically to replace p plus tx with a curve that's moving along the domain. Okay, so that feels addressable. I feel like we could all engineer a reasonable way out of that particular problem. We might have to do a little bit of the kind of proof we did a lot of toward the beginning of this course, where like, you choose some curve whose initial tangent is x, and then you want to triple check that, like, if I chose a different curve, my definition of derivative wouldn't change or something like that. But in any event, maybe we'll call this problem A. And there's a second issue, which I think is a little bit more subtle, and that is this minus sign here. Now, here's the basic point. Y evaluated at P, this thing, what space does this live in? It lives in the tangent plane at P of M. But Y evaluated at P plus Tx, or maybe in some point displaced away from P, but constrained to be on our manifold, this does not live in the same tangent plane, right? It lives in some tangent plane displaced away from P, right? If this is P here. And that's a problem, right? Because we really shouldn't be subtracting things that live in different spaces. So we're going to call this problem B, where essentially we want to compare vectors or tangent vectors at two different points. We need to come up with some reasonable comparison, and subtraction may not be the best way to do it, right? These are in different spaces. So for example, maybe I'm on now the sphere is another good canonical domain. And I have two different points, that are connected by a great arc. These 2 points have two different tangent planes. And we have to decide, like, what does it mean to compare a vector in this tangent plane to a vector at that tangent plane, since they only contain a very small, in this case, one-dimensional subspace in common, which is probably not enough for comparison. Right? So we need some mechanism for taking vectors at one point and dragging them back to be vectors at the other. And I think just the fact that I use that phrase, and given your homework 3, you can probably guess a pretty reasonable mechanism, which would be parallel transport. That would lead us to a notion of covariant derivative. So in any event, I think in general, you can understand many of the different definitions of what it means to differentiate a vector field on a manifold or a surface as basically different choices for criteria A and B above. Now, in today's lecture, we're going to talk about two different sort of key domains here. So let's try and dig in a little bit more. So again, to add a little bit more detail here, essentially we need to solve problem A. So remember, problem A is that we want P plus Tx to be on our manifold. So instead, to solve problem A, I think we would all agree to do the following, which is to use some curve gamma of t. Maybe I'll make it gamma subscript p, so just to make it really clear, where this thing takes some small interval around 0. We don't really care what happens globally into our manifold, and basically just traces out a curve with initial tangent x, right? So we're going to make sure that gamma of 0 is equal to p, and gamma p of 0 is equal to p, gamma p prime of 0. Remember, we're differentiating in the x direction, so maybe this is x of p. Then, if we want to resolve problem A, one way to do that in kind of a generic notational way would be to rewrite our derivative as follows, which is the limit as t goes to 0. Now, instead of y of p plus tx, we can write it in a different way, right? We can say this is maybe y of gamma p of t, like that, minus y of p. Notice this is the same as y of gamma of 0 divided by t. And now we've kind of solved problem A, generically speaking. Now, it might be that we want to choose a special curve gamma of p, and that's somehow necessary in a particular definition of a derivative, but I think we can all agree that this is sort of a reasonable, generic way to solve problem A. Again, my goal here is to give you this sort of generic formula for defining a derivative of a vector field on a manifold, and then we're going to go through two different examples and see that they lead us to different places. So how we're going to resolve problem A is by replacing the straight line with a curve whose initial tangent agrees with our vector field. Now, how can we resolve problem B? Well, essentially, what we need is some mechanism which is going to compare vectors at different points. So one very generic thing that I could do would be to define a function like phi sub t, which is going to take the tangent plane at gamma p of t. I guess really there should be a p on here somewhere. Maybe I'll put it there. But in any event, I'm going to take a point in the tangent plane at one point along my curve, and essentially what my mapping needs to do is tell me how to compare that to points at the tangent plane at P. Right, so parallel transport, which you guys worked through in your homework, and we're going to motivate again today, is one example, right? It takes in tangent vectors at some point on our surface and tells us kind of how to drag them back to our central point, because once we do that, now this minus sign makes sense, right? Because the minus, both vectors are going to end up in the same linear space, right? Tp of m. Okay, and so that leads us to an even fancier extension of the formula at the top of the slide from the one here, which is the following. We can write limit as t goes to 0 of phi tp at y of gamma p of t yep, minus y of p over t. Minus y of p over t. So as always, I'm working from my notes, which are sitting off the screen here. Okay, and so why did I do all the writing on the left-hand side? Basically, this is a way to start with this formula here, right? To start with this definition, I think we all agree makes some sense on how to differentiate a vector field in Euclidean space. And now we've sort of introduced two edits to that formula to lead us to this generic formula here, which is sort of a vague technique for how I might go about differentiating a vector field on a manifold. Now, why do I keep saying it's vague? Well, essentially, in order to really fill in a definition, I need to add two details. The first one is specifically what choice gamma do I make. Now, what we're going to find in many definitions is that actually really doesn't matter beyond satisfying these two properties here, but there are some where it will. And then the second one is that we're going to need some mechanism for transporting vectors around, or in other words, to compare different tangent planes to one another. And why? Well, essentially, it all boils down to making that minus sign well-defined, right? Because what we want is to subtract vectors that are in the same vector space, and the vector space that we care about is the tangent plane at P, right? So this generic sort of mechanism for moving vectors around is one way to sort of think about that, or at least to abstract it away in some function that we're going to define later. Yeah, like this is sort of the modular programming way that you might think about deriving a vector field derivative. So now let's fill in two different ways that we might add details to this formula. And the kind of funny thing is that we'll see it leads us to two different notions of differentiating a vector field on a manifold. So we're going to do this twice, and then we're going to go through some slides that actually illustrate what these two derivatives kind of look like. So first, I just want to give you a high-level idea of the story, and then we'll dive into some more details. So the first version of the story is something that we would call a Lie derivative, L-I-E. Okay, and so a Lie derivative is sort of one basic way to differentiate a vector field, and it's built on the idea of solving ordinary differential equations. So let's say that we think of our vector field x. Remember, this is sort of the thing that's giving us at every point the direction in which we want to differentiate y. Well, you know, we can think of it as maybe having some flow lines, right? So like maybe here is one reasonable version of x, you know, on the plane, like that. Okay? So in other words, we can always define what we might call an integral curve as follows. So, an integral curve is some curve on our domain, which oftentimes we think of as sort of a self-map, right? So, in particular, sort of a typical object that we might define, oftentimes is notated as follows. It's basically saying, like, if this is my vector field x, then this function phi t x of p, you can sort of debate which of these letters should go in which position here. But essentially what this is telling us is if I flow for time t along field x at p, where should it go, right? So maybe I start here, and then it's going to kind of trace along this curve for some amount of time, and then give me this image. So given a vector field, if I solve this ODE at every single point, so in other words, like, I take every point on my surface and flow it for the same amount of time t, what I get is a self-map which tells me after flowing along this field for this amount of time where everything goes, right? And that's like sort of the set of integral curves. Okay, so this gives us a toehold into our manifold. Now, in particular, or into our definition on the left-hand side. So notice that phi tx, considered as a function of p, you can think of as really a function from the manifold into itself. Do you see that? Like basically, do you see that? Hopefully you do, because I'm talking to myself in this room. I'm going crazy. This pandemic stuff is just a lot. Right, so our integral curve here is basically saying for every point p on our manifold, what I get after flowing for time t along our vector field. And you can think of that as a flow of the entire domain M into itself. In fact, under pretty weak conditions on X, this thing is a diffeomorphism. Okay, so let's say that this is the basic object that we're working with. One thing to notice, by the way, is that you can define this. You don't need a metric or anything else. Basically, you can get these integral curves by solving differential equation, right? So the way that you would do it is d over dt of phi tx at p. Well, what is this thing? Well, I flow p for time t along x, and then its rate of change should be x, right? So it should look like x, and you have to be a little careful about where you evaluate it. I guess it would be, hopefully I'm going to get this right. I'm doing this off the top of my head, so you guys should all check me. Something like that, right? So the basic idea here is that like the rate of change as p is moving along is I look forward along our field and evaluate the vector, right? So this is an ODE, and of course at phi 0x of p is just p, right? Because I flowed for 0 time. So this is a thing that I can get by solving a differential equation, and it actually needs no knowledge of metric or distance along our surface, anything else. This is purely a kind of topological thing. Whew. Okay, so once I've defined this integral curve object, now I can define a Lie derivative easily enough. And it looks something like this. So remember, we need to essentially fill in our two decisions, A and B. We need a way to move along our domain, and we need a mechanism for pulling vectors back. Okay? So how are we going to do that? Well, our decision for A is specifically to use the flow lines of X. Okay, so in particular, essentially I can say, well, gamma P, oops, never cease to amaze myself with being able to say one thing and write another. Gamma P of T, we're just going to say is exactly the integral curve here, right? So I'm going to just write it as phi T x of P. And notice that kind of by definition, this satisfies the two assumptions here, so we're good. And then decision B for our Lie derivative, how we're going to compare vector fields. This part is a little bit tricky. Remember that we actually defined the differential of a map between manifolds, like this operator D, which takes tangent planes to tangent planes, okay? So in particular, what we can do is say that we're going to define capital phi tp as the following. It's going to be the differential of phi minus t evaluated at gamma t, gamma p of t. Okay, so let's make sure that we understand what this notation is saying. Notice that both of these are just kind of reshapings of this basic integral curve object that we defined. Okay, so remember our two ingredients here. We need to draw curves along our domain so that we can compare y at different points, which are displaced along our field x, and then we need to pull vectors back. So in terms of drawing curves, what we're going to do is just flow along the vector field x. I think this is a pretty reasonable choice. In fact, I think this almost always works for most definitions of derivative. And then in order to compare vectors, remember that we computed the differential of a map. So in particular, oops, sorry, I forgot this superscript x. Remember that, what is phi? Phi is a thing that inputs a point on our manifold and outputs a point on our manifold. And it's obtained by flowing for some amount of time t along our field x. Here, this kind of minus t is basically saying, a different way to do it would be to put the minus on x here, saying flow backward in time. So why does this make sense? Well, here's kind of the picture. We want to compare our field y, so y is like some other object, like here's y at p, maybe. Oops, I guess p is up here, so maybe this is y at p, sorry. So here's y of p, and then y changes to some other vector as I move along the curve. So the first question we have to ask is, what curve are we going to move along? And the way that we do that is just flowing along our field x. The second one is, now I have two different points where I'm trying to compare tangent vectors. And I need to take this tangent vector here and kind of pull it back to the point p. And the way that we do that is by differentiating the self map that we get by flowing the whole domain along our vector field x. And if you go back, we actually defined what this thing is for just general maps from one manifold into another. In particular, this is a map from the manifold into itself. And so D of our map takes tangent plane at the target to tangent plane at the source, which is exactly what we need. So what is the Lie derivative doing? By the way, when we make these two choices here, there are many different choices of notation. One that I think we use in this course looks like this, which is the Lie derivative in the x direction of field y. Okay, so the Lie derivative is useful topologically, and it's kind of interesting. Essentially what it's telling you is that the only perspective we have on a field is by flowing along the field itself. So like, for instance, in this particular case, notice that phi here is going to kind of smush the manifold, right? Like our vector field is telling us to kind of squash things inward like that. So when we look at our map d phi, when it's going from here to here, it's going to kind of pull things back out. And so that's really what's going on, is the Lie derivative is kind of like the rate of change of our vector field y given by the perspective of the warp that's induced by the vector field x. We're going to see some pictures of this in a few slides, but hopefully you get the high-level point, which is that by filling in considerations A and B, like how to move along our domain and how to compare vectors at different points, we ended up with a derivative that we call the Lie derivative. And the main non-trivial piece here is B. The basic point is that we can get maps between tangent planes by taking the derivative of the self-map that you get by flowing along the field x. That was a lot of words to digest. You might want to pause that one and really mull it over. This is certainly something that I struggle with as a differential geometer. I feel like this definition is a bit abstract. So let's erase this and then make space for a different derivative. So here's a second way that we could have gone about engineering answers to questions A and B, which I think is sort of equally reasonable but doesn't use flows along our vector field in the same way. It actually leads us to a second derivative, which we'll call the covariant derivative. And now I'm going to make a bit of a derivative. I should tell you now that the way that I'm going to define covariant derivative is sort of the elementary, boring, embedded surface kind of way. Oftentimes, like the sort of axiomatic way of going about differential geometry might be to define a covariant derivative through its properties and then show that certain choices of covariant derivatives lead to different notions of geometry. That's a more advanced idea, but here we're just going to define one, which I think is the most common choice and corresponds to the Levi-Civita connection on a manifold. But although I guess actually I'm not going to use that quite yet. In any event, remember that we need two choices, A and B, ways to connect points together that agree with our vector field x, and then ways to pull back tangent vectors. And the covariant derivative actually makes an even simpler choice here, although it turns out to be sort of a little more complex to analyze. So in particular, it turns out for covariant derivative, it actually doesn't matter. I could use the same choice as the Lie derivative. But in fact, it turns out that we can use any curve on our surface that satisfies two properties. Satisfying these two things, right? That gamma p of 0 is equal to p, and gamma p of gamma p prime of 0 is equal to x of p. So in other words, we can actually choose an arbitrary curve so long as its initial tangent vector agrees with the vector field direction in which we're trying to differentiate. This is actually true for the Lie derivative too, but you kind of might as well use the diffeomorphism you get by flowing along x in the Lie derivative just for consistency and simplicity. The reason in the covariant derivative that we write it like this is that we'll find the covariant derivative, you can kind of compute it pointwise. So the Lie derivative, you need this sort of entire field to compute this thing because of that d phi term. So one thing that you can't do is say like, I don't know the value, I only know the value of x at one point. Whereas a covariant derivative, that turns out to be okay. Maybe I'll emphasize that point in just a minute. But now, rather than using d of the self-map that you get by flowing along x, here we make a very different choice for this mechanism of moving tangent vectors around. In particular, what we're going to do is to use parallel transport along our curve gamma. So this was covered in homework 3. We're also going to add some intuition later in today's lecture, but recall very briefly that parallel transport is sort of a way of dragging vectors along a curve while keeping it in the tangent plane at that point on the curve, right? So if I have, my manifold, I've got two different points that are connected by some gamma, and these points have different tangent planes. Then parallel transport is sort of a mechanism for dragging the tangent plane from one point to another without inducing needless kind of twist as we do so. And it's essentially gotten from this ordinary differential equation that you studied in your homework, which is to say that the projection onto the tangent plane at gamma of t of m of the rate of change of some vector as it moves along our curve gamma is 0. So in other words, like my gamma doesn't twist in the tangent plane as I drag it along my curve. I guess here it should be like negative t or something because I'm moving it backward, but whatever. But rather the only component of v which is allowed to change as I drag v from one tangent plane to another is the component that's sort of normal to my surface, because that's the part that I can't really do much about, right? Like I need to cope with the fact that my tangent plane is changing, or in other words, like in the surface case, the normal is changing. But I don't want intrinsically there to be like a lot of twists and steering wheel change. And so that's how you deal with defining the covariant derivative. Now, we're going to talk a lot about comparing Lie and covariant derivatives, basically for the rest of today's lecture. There's sort of a few key points here. both of these objects are do the following, which is that they input two vector fields and they output a third, which is the derivative of one vector field in the other vector field direction. But that's a little bit of a false way to understand these two derivatives. It's absolutely true for the Lie derivative. Now, the Lie derivative is saying, you know, I need a vector field x and a vector field y, and then I output a third vector field, which is, you know, Lxy, which is the derivative, a vector field which at every point can be interpreted as differentiating y in the x direction. That's perfectly fine, but it turns out that you kind of need to know all of x in order to do that because of the diffeomorphism sort of flow along the field definition that we introduced before. That makes some sense because essentially remember that we had that d phi in that definition, and phi might squash stuff, and you need to know sort of where more than one point goes in order to measure that squash. The covariant derivative, it turns out, is kind of interesting. By the way, oftentimes I guess we notate it like this, which is that I only need to know, if I want to evaluate this thing at a point P, I need to know y everywhere, but whereas in the covariant derivative, I also needed to know x at every point on my manifold. For the Lie derivative, rather. For the covariant derivative, it's enough for me to just know x at P. This is a critical difference between the Lie derivative and covariant. The Lie derivative, I need to know the entire x vector field so that I can compute that flow of my domain and differentiate it. But in this definition here, notice that like all I really needed was x at that initial point so that I knew how to draw my curve gamma, and then I parallel transport stuff backward. So this is a big difference between Lie and covariant derivative. And I think it means that covariant derivative and somehow is more intuitive and natural to think about, which is that really the only information I need to get the derivative at y at P is x of P. So in other words, like differentiating at P and differentiating at some other point are sort of independent operations, right? Gotten by, again, move along a curve, parallel transport backward. If instead of parallel transporting backward, I differentiate a flow of the entire surface along my field, then what I end up with is the Lie derivative, and this information is no longer sufficient. I need x on the entire manifold in order to define it. Now, both of these definitions are reasonable, and it turns out they just appear in different places. The Lie derivative appears all over the place in physics. It's topological, meaning that it doesn't need the metric of the surface, whereas the parallel transport really, because you have this projection operator here, really fundamentally needs you to be able to measure lengths and angles in order to drag stuff along the surface. That makes sense, right? Like I need angles in order to make sure that I have this sort of minimum twist drag of a vector from one point to another. Covariant derivatives tend kind of to appear in geometry constructions and Lie derivatives in topological ones. Now, this is a sweeping overgeneralization, but basically I'm just trying to give you some idea of why this sort of basic definition of differentiating in Euclidean space actually doesn't suggest one way to differentiate vector fields on a manifold. There are at least these two, right? This Lie derivative and covariant, which are basically obtained by different choices for B, like flowing the manifold along the vector field and then differentiating it, that's what gives you Lie, or doing parallel transport, which gives you the covariant derivative. Lie derivative needing the entire vector field at once so that you can unsquash stuff, whereas a covariant derivative is independent from one point to the next. Okay, so hopefully I've managed to confuse you all. Now let's draw some more pictures and really think about this in more detail. All right, so the next couple of slides here are basically just filling in illustrations of what we sketched out on the board here with a little bit nicer visualization. So to start, we'll talk about the Lie derivative. So remember that the Lie derivative is basically built on this sort of diffeomorphism. I'm afraid I called it phi on the board and now it's psi. Sorry about that. Where essentially given a vector field V, in this case, we can come up with a self-map of my manifold onto itself, which is given by solving the ODE where the flow is given by V. Right? So the idea here is that the vector field is telling me how to flow the surface along itself. There's actually kind of a nice group structure here, which is illustrated underneath our equation, but that's not going to matter a whole lot for today. And so our Lie derivative was built on this sort of vector field flow-based construction. Incidentally, these flows are useful for lots of things. Something that we're not going to cover in this course is that they're used to construct objects called killing vector fields, or KVFs, which are vector fields where when you flow the surface along itself, the geometry doesn't change. So think like a roll of toilet paper. You know, if I flow a cylinder along itself, the metric remains constant, like it doesn't stretch or bend. Only very special surfaces admit killing vector fields, but there's a whole literature, actually. My undergraduate thesis was sort of involved in the ground floors of this work, which really was started by Miri Ben-Chen and Adrian Butcher, which involves constructing approximate killing vector fields on domains that don't admit them. Right? Only very special surfaces have these sorts of things. But in any event, this idea of a vector field flow gives me a self-map where, like, I take my domain and I flow it, like in this case, just rotating my toilet paper tube. And so I can differentiate that as a map from a manifold onto itself, and that was our basic object for defining the Lie derivative, right? So again, as a reminder, basically the construction that we did on the board, the Lie derivative of in this case, of field W in the V direction, evaluated at P, that's how you read that expression on the left, is given by the expression on the right, where you kind of look at the differential of the self-map that you get by flowing along V, of W pulled back through d psi here. And this is just one reasonable way to fill in those criteria A and B that we wrote down before. Again, the main thing you should get out of this lecture, and quite possibly this course, is that it is not pronounced lie in this case. It is the Lie derivative. It's also not Euler, it's Euler, just FYI. But that's, you know, now we're done with my main mathematical complaints. You know, if there's one thing that you can get out of this course, it's how to read mathematician names, although I'm sure I'm actually not doing a great job of it either, since I don't speak French, Danish, whatever. In any event, the Lie derivative shows up all over the place in physics, continuum mechanics, and so on. It's a very basic object, but it does have some counterintuitive properties, specifically as a derivative. So there's a bit of an illustration of it here, where I can actually take a constant vector field W, and it might not even look constant with respect to the Lie derivative. And the reason for that is that the Lie derivative also sort of takes into account the squash and stretch, which is implied by the vector field V. So here's an illustration of a really funny phenomenon where this can happen. So here my vector field W, I guess, is this constant blue vector field. And the issue is that if the flow lines, I'm noticing, by the way, on the slides that there's like X, Y, V, W, but if the flow lines of V are sort of converging toward one another, then actually the vector field the vector field W looks like it's changing length because you're sort of warping it out based on the flow lines converging. So as a notion of derivative of a vector field, Lie derivative is kind of a weird one to think about. Like even things that we would think might be constant along the plane actually look non-constant with respect to the reference frame that V is sort of providing in this construction. And so kind of motivated by this weird property that like even constant fields might not have zero Lie derivative if the field V here is like converging or stretching or whatever, that sort of leads to one motivation for why we might want the covariant derivative. A different motivation related to something else we wrote on the slide is that usually when we think of derivative, what we're really thinking of is like, what is the derivative of the orange field in the blue direction, right? Like that kind of a question. And the Lie derivative actually really doesn't answer that question. This is a bit of a subtle point. In particular, in order to define the Lie derivative, we need not just the blue field at a point P, we need the blue field on the entire domain, right? Like for instance, in the previous slide, we needed to know the fact that our field was converging, which required more than just one flow line. The covariant derivative, on the other hand, allows us to answer queries like this. So in other words, I don't need an entire blue vector field in order to differentiate one vector field and another. I could just fix a single point P and differentiate the orange field at that point P using covariant derivative. If this is a subtle point and one that like takes a little bit of time to digest, it's for two reasons. One is that I'm phrasing it poorly, and the other is that like it's genuinely difficult and tough to wrap your brain around. These are really subtle topics that I think the first time around really, like, all these derivatives kind of look the same, but there's like very small shades of difference that turn out to really, really matter here. So in order to answer queries like what we have on the screen here, the mechanism that we use, which conveniently we introduced on homework 3, is parallel transport. So if you remember from parallel transport, it's basically a canonical way to identify tangent spaces at two different points, really I should say 2 points connected by a curve. And the way that we defined parallel transport on our homework was using a particular ODE, which said that as I drag a vector, in this case u, along a curve, it needs to stay in the tangent plane. That kind of makes sense. In fact, in the Riemannian version of the story, there isn't even an extrinsic space where the vector could live. And moreover, that the component of change of our vector in the tangent plane is 0. So in other words, kind of like my vector isn't needlessly kind of spinning around in the tangent plane as I drag it back. The only component of its rate of change is out of the surface. And so this gives us a unique and sort of canonical way to identify tangent planes with one another. It's actually a linear map given 2 points connected by a curve. Incidentally, if that curve changes, then the parallel transport map will change as well. In fact, you sort of showed that on your homework. So that leads us to a means of defining a covariant derivative. This is a controversial definition because it is relying on the embedding of our manifold into a Euclidean space. There are ways of going about doing this axiomatically on a Riemannian manifold without relying on the immersion here, but in this class this is good enough, where we can write the derivative of a field W in the v direction using this expression at the top of the slide, where what I do is I differentiate W just thought of as x, y, z coordinates, which I can do because my manifold is embedded in 3D, in this case for a surface, or in general embedded in Rm. So I can differentiate it in the v coordinates, and what I'll get are just the rate of change of the x, y, z coordinates of our vector field as I like draw a little curve in the v direction, right? So that's what this dw of v is. And then what we do is I just take that vector, which may not be parallel to the surface, and I just project it back down onto the tangent plane. So a different way of understanding this definition, which is the second equality here, is that I take a curve alpha, which goes through P in the v direction, and I take W composed with alpha, right? So this is like just looking at the vector field as I walk along the curve alpha, and I differentiate it at time 0. So I look at the infinitesimal sort of change of my vector field as I move a tiny step in the v direction along my manifold, in this case my surface. And that can have two components. It can have a normal component and a tangential component. The covariant derivative is just the tangential component of that. This is very similar to how we went about defining curvature and so on, right? Like, remember that we like define curvature of a surface, second fundamental form, by essentially taking the rates of change of different vectors and so on a manifold, and then just projecting them back onto the tangent plane or onto the normal space. And basically, this is an extension of the same logic. So this is our definition of the covariant derivative. And notice that it's very similar to the Lie derivative in that I move along the v field and observe how the field W changes, but the way that I pull back things is different. In this case, I do it by like kind of dragging things with parallel transport or equivalently projecting onto tangent plane, whereas the Lie derivative did it by looking at the entire flow of v, which might like compress or stretch based on v at more than one point. And this is specifically the Levi-Civita connection associated to our surface. There's a sort of more general version of covariant derivative. If you read through Riemannian geometry textbook, that sort of takes this basic intuition that we can develop with this simple definition for an embedded manifold, and then tries to make it work for a non-embedded sort of Riemannian structure. And basically, all these properties here, we're not going to go over them in detail, but they basically verify that the covariant derivative really behaves the way you might expect a derivative to behave, that somehow it has a product rule, it's linear, And also, it's sort of well-behaved and linear, not only in both of the inputs here, in this case, v and y. So I encourage you guys to do some more digging and reading here. There's so many different ways to sort of skin a cat here in terms of what's a definition and then what's a consequence of your definition, right? Oftentimes there's just a bunch of equivalent stories. These sort of 5 properties of a covariant derivative are sort of a nice way to define a covariant derivative object, or more generally a connection, which is basically giving you some means of making tangent planes talk to each other. If you like this kind of story, I encourage you to go talk to your TAs, David and Paul, who are really experts in this universe and have used it to great effect in their own research. Now, on the slides here, I've included a bit of a challenge program, challenge problem, which is lifted from Lee's Manifolds textbook. Basically, to just sort of, by the way, this Lee is L-E-E. It's a different Lee than Lee derivative. If you're looking for just a good way to kind of wrap your brain around all the different notions of covariant versus Lie differentiation, it turns out just even on the plane you can cook up examples where they're different. And I encourage you to kind of think through this exercise as a challenge, especially if you're interested in differential geometry. So now let's go back and revisit some formulas that we've already seen in this course, just to see that they kind of fit nicely into our definition of a covariant derivative. So, for example, remember that we defined geodesics, or at least local geodesics, using the ODE on the slide here, where we took the second derivative of a curve along a surface and asked that the tangent plane projection of that second derivative is identically 0. That's sort of what defines a geodesic curve. But projections of vectors onto tangent planes really is code word for covariant differentiation, so we can write a much slicker formula for exactly the same geodesic, and this formula is the basic definition that is also used in Riemannian geometry. Similarly, if you revisit the definition of parallel transport, you can kind of think of it as the covariant derivative of field V along a curve in the curve tangent direction is identically equal to 0 if it's being parallel transported. This is only independent of the path in the case where your domain is flat, but more generally, parallel transport is path dependent, and it's basically a way to drag vectors along a surface. So in the slides, I've included this link to this little video, which shows what happens as you kind of drag a vector along a triangle on a sphere, and you'll see it doesn't end up where it started. So I encourage you now to kind of go back to homework 3 and just revisit that same story using this nicer notation that we've developed today. As this one additional vocabulary word, which you've actually already seen on your homework, is this idea of holonomy, or holonomy. I never know the right way to pronounce it. We can take a vote on Piazza in our course. Which basically is measuring curvature as sort of, understanding curvature as path dependence of parallel transport. So for example, on a flat manifold, one thing you'll see is that parallel transport is actually not path dependent. Like if I take a curve from a point back to itself, parallel transport will just be an identity map. Whereas on a curved domain, that's no longer the case, and you can actually sense Gaussian curvature through precisely this construction. So I'll let you visit that on your homework now that you've been equipped with a little bit more language. Okay, so for the last little bit of lecture, or maybe even just some extra content you can watch at home, you're watching it all at home, but for some extra content we might not watch during class time, I thought I'd highlight a few extra kind of theoretical properties of vector fields that end up coming into play in the practical universe that I thought would be worth just mentioning and sketching out, even if we don't have the time to develop them rigorously in this course. One of them, specifically in 2 dimensions, is understanding the topology of a vector field. And this is a really beautiful theory. There's a really nice textbook titled Differential Topology. It comes from authors here at MIT, Gilliman and Pollock, which really goes through this theory in a lot of detail and has really beautiful illustrations. But basically, vector fields have a lot of topological structure which is intricately linked to the topology of the underlying domain, specifically for surfaces. And the typical lens that we understand vector field topology is through its singular points. So a singular point is kind of just where, usually we think of it in the differentiable case as a point where a vector field goes to 0 just locally. And in that case, you can kind of count how a vector field circulates around a given point. And what you end up with is basically something called the degree of the field. This is very closely linked to the winding number that we introduced all the way back in lecture 3. So the degree of a vector field is kind of understood by drawing a loop around a singular point and looking at the number of times that the field circulates around itself. And that leads you to this notion of degree or index. And there's this really central theorem, which is called the Poncare Hop Theorem, which says that in a vector field with isolated singularities, xi, if I add up all of their indices, what I'll actually get is, once again, the Euler characteristic of my underlying domain. Now, essentially, the Poncare Hop Theorem is going to be one of these beautiful structures that we're going to be able to preserve in certain discretizations of vector fields when we construct them on triangulated domains, which is pretty cool. In fact, some of my own research a couple years ago really makes kind of heavy use of this particular property. This is also just one of the central theorems of differential topology, that if I add up the indices of the singular points of a vector field, I get a topological invariant. Notice that chi for a sphere is non-zero, which actually leads to a very famous corollary known as the Hairy-Ball theorem, which says that if I take a sphere and I put a tangent vector field on it, necessarily, if that tangent vector field is smooth, it has to vanish somewhere. So a different way of putting that is if I have a ball, like a tennis ball, and I cover it in hair and kind of comb it flat, necessarily somewhere there's going to be a tuft. In fact, in the middle of the slide here, I show you a really interesting construction. So it's very easy to make a sphere with two tufts on it, like what you see on the upper left. You can actually make a vector field with only one tuft on a sphere, which is illustrated on the right, but that construction is a little bit subtle. Now, a donut has a different Euler characteristic, which actually allows for a tuft-free hairy ball. In this case, not a ball, I guess a hairy donut, which is quite simple. Like if I put hair on a donut, I could just kind of comb it flat by combing it along the outer loop of the donut. Now, a different construction which is also important and valuable in practice is not just to talk about vector fields, but also to talk about direction or directional fields. This specifically has been very well studied in 2 dimensions, and I encourage you to take a look at this really nice state-of-the-art report for a really detailed treatment. So the basic idea of a directional field, at least in 2D, is that I can think of a directional field as attaching like maybe 2 tangent vectors at every point on a manifold or on a surface. And why does that matter? Well, it turns out that the topology of direction fields is somehow different than the topology of just vector fields. Now, if we think of vector fields as tracing out flow lines, then a direction field, like maybe having 2 vectors attached at a point, now traces out like multiple flow lines. And that could lead to some really interesting things. So your instructor really struggles to draw pictures of this stuff, but let me see if I can try and do it successfully. So let's say, as a really simple example, that I construct a direction field which kind of looks like a grid, except in one quadrant. This pen is running out on me. Let me pull some ink out of it. Okay, so if I draw this direction field, right? So this is, you can think of this at every point on the plane as having 2 vectors which are orthogonal to one another. I can extend this direction field as follows. So here, away from this point, like maybe I cut this point out or I allow my field to have a norm, so it just goes to 0. This is a field of 2 directions per point on the plane. Do you see that? So like for instance, here the direction is maybe up and to the right. Or in general, maybe this is a 4-direction field. So it's up, down, left, and right, like that. Now, why did I draw this particular picture? So notice that, like at this point, our directions would look like that. Right, so this is a 4-direction field. Now, this illustrates the sort of basic challenge in computing these direction fields, which is basically representational in nature. And here's what I'm talking about. Now, if you look at this direction field and you ask, like, how do you represent it? Well, one naive guess might be to say like, okay, well in some sense maybe there's 2 vectors or 4 vectors here. So maybe what I do is I just think of, being v1, v2, v3, v4 as like 4 different vector fields, which are just like the up, down, left and right direction at every point. And indeed, for the most part, I could do that, right? Like I could take v to point to the right everywhere. And initially that feels like an okay thing to do. But actually in this picture here, despite my bad art, I think I've managed to draw a case where that's actually not possible. And here's what I mean. So let's say that I take a point here and I label the direction going out and to the right as my direction v. And now I'm going to draw a loop around this central point. And I'm going to trace what happens. So here it points to the right, it points to the right, and it's going to start moving radially as I move around my loop, right? So now it's pointing up. And now I continue my loop over and it points up like that. And by the time I got back to my starting point, notice that my field rotated 90 degrees. What does that mean? That means that this representation of thinking of a 4 field, like these these 4 directions at every point, actually kind of failed me thanks to the topology that I've set up here, right? I went around the singular point that I've constructed, and what I used to call maybe v1 like turned into v3. So the reason for that is that I have 4 directions, but I haven't labeled which one is which. This would be called combing. And at singular points, combing isn't always possible due to this phenomenon that I've just drawn, where I started by labeling on the right and then kind of smoothly following that vector that points to the right around a loop, and I ended up with a vector that pointed up. This is also like sort of another instance of holonomy around a singular point here. So instead, a lot of the hard work that happens in direction fields is to come up with representations that sort of glue together these 4 directions in a way that doesn't label like up is direction 1 and down is direction 2, and instead just thinks of them as 4 different directions at a point. So for example, in 2 dimensions, if I want to represent a 4-direction field that is orthogonal, so I think this is sometimes called a frame field, so like an orthogonal, orthogonal set of 4 directions. One way to do it, right? So in that case, that would be like, a vector v, another vector minus v, and then an up and a down, which are rotated here. So like v perp and minus v perp. Suppose that I wanted to represent this 4-directional object at a point in the plane. The curved version isn't much more complicated than that. One thing I can do in 2 dimensions specifically is I can identify the tangent plane with the complex numbers like that. And essentially, one cool thing that I can do if my directions are orthogonal to each other in this 4-direction case is instead to look at the v to the 4th power as a representation of all 4 of these things. One thing that I let you convince yourself at home is that all 4 of these complex numbers in the complex plane have the same 4th power. Like obviously minus v to the 4th has the same 4th power. Rotating 90 degrees has to do with like multiplying by the complex number I. So that also has the same 4th power. So one magic trick that we can use to represent this field would be instead to represent the 4th power of this set of 4 vectors if they're constrained to be orthogonal to one another. So in other words, basically there's some mapping from this onto a vector field which we'll use our representation. By the way, notice that the application for this kind of thing is like that quad meshing thing we talked about at the beginning. Or another fun vector directional field representation, which was introduced just a couple of years ago, was something called a Polyvector Field. Let me erase to make some space. So this polyvector idea, the basic point was that sometimes on a domain, like in these meshing applications, we have some tuple of tangent vectors, and we don't want to think of them necessarily as like orthogonal. Like maybe it's just this set. But we also don't want to number them off thanks to those topological challenges that I talked about before. Like if I go around a loop, the numbering might change. So like let's say that I have 4 vectors, v1, v2, v3, v4, And I want to encode all four of these things, but I don't like the fact that they have numbers attached to them because the numbering might change. I want basically an order agnostic representation of four vectors. I guess on the slide here I've written them as U1, U2, U3, and U4. So I'll be consistent. These are U's. So once again, because I'm in 2 dimensions, I'm going to think of these as complex numbers, like that, where essentially I'm taking one direction and identifying it with the real axis in another direction and identifying it as the complex axis. Now, one thing I can do is define a polynomial on the complex plane. I'm going to call this thing f of z. And I'm going to write f of z as follows. It's just z minus u1, z minus u2, z minus u3, z minus u4, right? So and I'm going to think of this as just a function of a generic value z. Now, one thing I can do is take this polynomial, right, this product of 4 things, and expand it out, right? And when I do that, I'm going to end up with a giant product. So for example, I'll end up with z to the 4th power, and then the z cubed is going to end up being like minus, I guess, u1 plus, right? So I have minus u1 times z times z times z, minus u2 times, and so on, u2 plus u3 plus u4, z cubed plus what's going to be the coefficient of z squared. It's going to be like, you know, u1 u2 plus u1 u3 plus u1 u4 plus u1 u2 plus dot 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 z squared. Notice that these are like higher and higher powers of u, or not powers, but products. Plus like u1, u2, 2u3 plus u1, u2, u4 plus dot 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 z plus, and then the very last term is very simple. Oh, by the way, so some of these should have minuses. I guess that'll be a minus. And then plus u1, u2, u3, u4. Okay, but the details don't matter a whole lot, despite my having messed them up a bit. What matters is the fact that I'm going to take this polynomial function f of z, and I can write it in 2 different ways. This way is the factored form, but I can also take the polynomial and just expand it out. And essentially, what I'm going to do is think of these as sort of coefficients. So like, I can think of this, I'm just going to call this A3 maybe. Call this A2 and so on. So what ends up happening? Well, at the end of the day, I can take any polynomial of this form, and just by expanding it out, there's some equivalent formula that looks like, in this case, because I have 4 things, that'll be z to the 4th plus a3 z cubed plus a2 z squared plus a1 z plus a naught. And that these are sort of in bijection. That, like, notice that obviously if I reordered the u's here, I would get the same a's, right? All that matters is where the roots are. So the basic trick of polyvector fields is to say, okay, rather than using these complex numbers to represent my field, which depend on the ordering that I've chosen for my 4 vectors u1, u2, u3, and u4, I'm going to instead use a different set of 4 complex numbers to represent my field. So I can think of these as just like literally 4 different tangent vectors. But those 4 tangent vectors are actually agnostic to the ordering of my roots. So this is just like a different way to encode 4 points on the plane that doesn't care about their ordering. So this is the basic trick for these polyvector fields, is like I want to store multiple tangent vectors on a surface, but I don't care about their ordering. I don't want to call the first one vector 1, the second one vector 2, and so on. So the way that I can encode them up to ordering is to go through this calculation and store these coefficients rather than the roots themselves. And going back and forth is just like a root finding or multiplication problem, both of which are very well established numerical things. Incidentally, one thing you might notice is that these expressions have nice names. These are called these symmetric polynomials. And this is just like another way to polynomials. Encode a set of complex numbers without caring about their ordering. So I'll let you guys read this paper for some more details. This is one of these things where it's a really, really simple, insightful idea, and something that I think is really fun to contemplate as we go along. Okay, so since we're low on time, I think I'll defer into an extra lecture segment discussion of sort of an extension of this polyvector field idea to higher dimensional problems. Essentially, the construction that we did here really depends very strongly on the fact that we're in 2 dimensions, right? We use this complex number trick to encode a set of vectors. Your TA, David, has worked very hard on representations of fields that are agnostic to ordering in 3 dimensions, and we'll see it's a very different story leading to an object called an octahedral field. That's sort of a research topic and a very modern idea in geometry processing, so we'll save it for an extra optional segment in case that's of interest to you all. But for now, hopefully you have a good idea of the sort of high-level aspects of what it means to develop a theory of vector fields in the differential geometry universe, as well as some of the interesting extensions that matter, like frame fields, for the applications we care about, like quad meshing. So obviously, this is a really superficial lecture just to give you some idea of like what a Lie derivative is, what a covariant derivative is, why they're different, why we need both, and so on. I really encourage you to dig through both the applied literature and your favorite geometry textbook to get a better perspective here, because this is just so much interesting, deep content that's hiding underneath what we're just spending one lecture on. But with that, we'll conclude for the day, and next time we'll talk about how to make some of this theory work in discrete applications in numerical universe. So I'll see you next time.